Welcome back, cutters, and all those who like doing a little bit of tech talk on a Sunday afternoon. Okay, well, welcome everyone, and yes, this is yet another Toolbox Tech Talk reboot. For those who are new to the channel, I did this all during COVID lockdowns in Melbourne, and then had a bit of a break when lockdowns finished, but I'm back. And I'm back because I enjoy talking to people. B, I think there's a lot of information that I can share with solar people, whether you're a solar designer, a solar installer, a solar customer, or just someone who's interested in the tech itself. So there you go. That's kind of my audience out there. Now, I'd love to know who's listening, who's watching, so just type in the chat if you like. It'd be really great. Better press go live here. Okay, so we are going live. So that was I just did a whole spiel before pressing go live. So let's start again, Glenn. Welcome everyone to Toolbox Tech Talk. And geez, I'm a dummy. There's so many buttons to press sometimes, and there I was chatting away to nobody and didn't go live. But I'm live now. So welcome everyone to Toolbox Tech Talk. For those who are new to the channel, this is all about solar technologies, particularly the renewable energy side of things, solar PV, solar batteries, inverters, and associated equipment. That's kind of what I'm looking at. And also, very importantly, Australian standards, which is something I'll be talking a bit about today. Definitely quite a bit about standards, but also a bit about the understanding how a solar PV panel, a photovoltaic panel works, and how you design for optimum performance and safety. And that's all about understanding IV curves. So we'll get into that. I'd love to hear where you're from. So just if you're watching, jump in the chat and say something to me. Be nice to know what country, region, anything you like. Just say hi in the chat there. So that'd be great. Now, I'm going to take questions throughout the live stream for the next hour or so. So feel free to jump in there and
standard I'll be talking about definitely quite a bit, but also a bit understanding how a solar PV panel works and how it...
Well, that's my little annoying friend called Siri. Sometimes she's quite good and sometimes she's a bit of a pain. So I'm just going to tell Siri to chill out and not talk to me. That was a bit of a dumb moment. So here we go, turning off Siri, and she's really hard to turn off sometimes. Okay, I'll put her in a bottom drawer. All right, well, there's a bit of a stumble start. So welcome everyone, and a bit on the live streaming technology too. So the reality is that when you watch a YouTube video that's pre-recorded and been uploaded to YouTube then does a whole lot of optimization on that video, and mostly it's about compression. So it can compress the video so that people can watch it at different resolutions depending on the bandwidth that they're at. But when it's a live stream, it just goes hard. It basically just streams to you at the full, and at the moment it's 5 megabits per second. So if your feed's not really up to it, you'll get a bit of a little bit of jittery kind of reception. But not to worry. This is saved and you can watch it immediately after it's finished. It will be optimized by YouTube, so you can work your way through it and not worry about any little hiccups in the live stream. So let's keep going. Just checking my systems here. I usually start with some general stuff, and I've got something for the Kiwis watching this live stream at the moment, and it's a bit exciting because after 10 years of living with outdated standards and lobbying government, including myself directly lobbying the minister, the new minister, Simeon Brown, at a conference in Auckland announced that he'd do something about it, and now he's really announced something he's going to do something about it. He is going to update New Zealand standards for solar EV at the top of the list, and a whole bunch of other standards as well. So New Zealand's going to do a big 10-year catch-up. It's proposed to be gazetted in April next year. Fingers crossed on that one. That will be really fabulous. So, yeah, it's really big news for New Zealand. In fact, I'm off to New Zealand tomorrow to run some training courses for solar installers and electrical inspectors. And oh my gosh, it's been such a difficult time for installers to know which standard to follow, because they were gazetted way back in 2010, so they had to follow the old standards. We've had multiple updates since then, but they weren't referenced in New Zealand electricity regs, so they couldn't officially be used without some special exemption that some people chose to get as well. But now it looks like you're just going to play one big catch up, and it's a very good time to catch up, because our solar standards, our joint solar standards between Australia and New Zealand, are getting quite mature now. So 5033, the PV array standard's been out for nearly 20 years. The inverter standards similarly, and it's had significant updates throughout that period. And we've just announced the latest update to the inverter standard for inverters connecting to utility grids or supplying power to installation, 4777 Part 1 2024. And the big news for those who have been under a rock is that 1,000 volts for domestic is now cool. So that's a really big woohoo moment, because we've had 1,000 volts in our PV standard, but you had to line up with our inverter standard before it could really be applied for domestic installations. Yes, okay, well, I see there's a few people joined in watching, but no one's in the chat. I'd love to see a few words thrown at me to say hi, yeah, where you're from, any questions you might have around kind of solar and batteries, etc., and standards. Just throw them into the chat. Yeah, so that's the news. New Zealand is playing catch up, and about time. So really fantastic. What I really want to cover today is two main topics. One is understanding IV curves, and the reason for that is so if you're designing a photovoltaic system, you need to know a couple of things about how the PV is going to work, particularly when it comes to temperature. So looking at things like the maximum open circuit voltage. Now you might think, oh, that's an easy one, Glenn, because 5033, table 4.1, I think it is, says just pick a temperature range and there's your multiplier. Yes, you can do that, but it's a dumb idea. Why is it a dumb idea? Because that multiplier hasn't changed since the original version of 5033, but modules have got much better at reducing power loss and voltage rise with temperature change. Well, voltage rise when they're cold, I should say, and power loss when they're hot. Those two things at either end of that linear spectrum of coefficients. So if you use table 4.1 in 5033, it's fine, but it's not the best way. In fact, it's probably not in your interest if you live somewhere quite cold. So if you're in the southern states of southern states of Australia, or certainly the South Island of New Zealand, you may be able to put an extra panel on your string just by using the right formula. So that's what we're going to look at next. So let me bring it up. Now, it all starts with a data sheet. You need to understand a data sheet. And the data sheet tells you the performance of a module at standard test conditions. Now, g'day, I just saw something in the chat. Charles from Waiheke, part of the catch-up country. Hey, go Charles. That's right. Look, I'll tell you what would be even better if Simeon Brown said, bugger having to reference it in New Zealand electricity regs, just allow it to update like Australia does. When it's published, it's published. Don't have to go through another level, because remember, New Zealand's on the committee. New Zealand actually helps make the decisions of what's in the standard and any modification for New Zealand. So having an extra step to get the government on board, it's just a waste of space. But anyway, that's how it works. So back to this table. So this is with every solar PV module, you'll get a data sheet, and the data sheet will have these numbers. In fact, most of those numbers, the ones that I've highlighted in colour at the top there, are actually on the back of the module as part of the mandatory labelling. So the mandatory labelling includes things like what the power rating is at standard test conditions, which is a cell temperature of 25 degrees Celsius, which is pretty hard to get, by the way, have sun shining on a panel and it's still to be only 25 degrees Celsius. But that's what standard test conditions are, because it's kind of convenient for test labs. It's a nice room temperature. Then we've got things like voltage at maximum power. So this is really kind of the sweet spot where the panel is producing the ideal amount of voltage and therefore the ideal amount of current to give you that number there, 475 watts. The ones in green is about operating current and short circuit current. We'll come to those in a bit. And open circuit voltage is when there is no current flowing, you've just got voltage. And it's always significantly higher than the operating voltage. So there's those numbers. Now down here, we'll get to the series fuse rating, but we're going to be using these coefficients here, particularly to start with understanding VOC. It means voltage open circuit. And like I said, you can be lazy and just use table 4.1 out of the standard, but it's not in your interest because the default temperature coefficient in 4.1 is 0.45%, minus 0.45% per degree Celsius. Panels these days are approximately half that now. That means there's half as much voltage change with temperature as there used to be, and therefore, particularly under colder conditions, you get much less voltage rise. And that can mean you can put more panels on, so that's pretty cool. Okay, let's jump into a bit of drawing at this point. Okay. Oh, actually, I might just bring up one more slide. So here's an example of IV curves, and this is from the same data sheet. By the way, that was for a Jinko 475 or series module from probably a year or so ago. And what we've got here is these horizontal lines is the IV curve. So I for current and V for voltage across the bottom here. And the I at 14 amps is effectively the highest current that it will produce. Its short circuit current is up here at 14 amps roughly. But if you multiply voltage and current together, so at 14 amps and 0 volts, you've got 0 power. So therefore, this red line is the power curve of that 14 amp, starting at 14 amps IMP or ISC. And you'll notice the power is peaking, and that's the point that you'll get standard test conditions reading. So it'll say 475 watts, but it's only at this point here. So at this point here, if you drop straight down, you'll find that your current now is not 14 amps, it's a bit less. And also your voltage is not sort of 40 something, it's really down here somewhere around the 35 mark. So this shape of this curve really tells you the operating line of the module. Now at lower irradiance, current drops proportionally. So pretty proportional down to about 200 watts per square meter. So this is at 1,000 watts per square meter, sort of 800, 600, 400, and at 200 watts per square meter, which is a fifth of what we call a peak sun, now we are starting to see the voltage droop quite a bit for open circuit. So it droops a little bit. And also you'll notice that the maximum power point is fairly static. It's just still drifting a little bit. It's not a problem because one of the beautiful things about inverters is they have a maximum power point tracking charge controller built in. And it dynamically finds this spot here, the peak point, or I should do the IV curve, the peak point on the IV curve where the sum of voltage and current gives you the most power. And it does it by experiment, literally. It starts at open circuits, so first thing in the morning, the sun comes up, there's a peak voltage appears on the panels, but no current is flowing. So the inverter's just waiting for the voltage to get to its switch on point, which typically, for a single phase inverter is 100 and something volts, and then it'll switch on, it'll start to draw current. So the inverter is a smart load. It's actually drawing a small amount of current to test if there is really any energy out there in the sun, and if there is, it keeps drawing current. So it keeps tracking along the IV curve going, volts times amps equals power. Am I getting more power? Yes. Keep tracking along this line. More power? Yes. More power? Yes. More power? Yes. Oh, less power. I've gone too far. Go back. More power? Yes. More power? Yes. Less power. Oh, too far. Go back, right? So it's tracking back and forth, literally, doing a little what they call perturb and observe. Change stuff and see what happens, and then keep trying to find the sweet spot. Why doesn't it just lock onto that sweet spot? It changes all the time with temperature and irradiance. So as the sun goes behind a cloud, it drops down to here. So it's moved a bit. And behind a cloud again, it moves a bit further over here. And it's always moving quite a bit. So that's what a maximum power point tracking charge controller does. And this is just a simple representation of the amount of change for 3 parameters: short circuit current, ISC, open circuit voltage, VOC, and power max, so the maximum power. And you'll see cell temperatures across the bottom. Now, it's very important to remember, we're always talking about cell temperatures. Doesn't really correlate with air temperature. So a PV cell has a similar thermal rise characteristic to metal. So you put a tin roof in the sun and it's a 20-degree day, that tin roof will not be 20 degrees. It'll be way hotter. So the specific heat value of the metal means that it will gain heat quite significantly from ambient. And the same is true of a solar cell. It'll be a lot warmer, typically 25 to 35 degrees hotter in full sun than the ambient temperature. So we always talk about cell temperature when we're referencing any of these characteristics, voltage, current, or power. In the case of voltage, the safety numbers is about the highest voltage, and you'll see that the voltage actually rises as temperature of the cell drops below 25 degrees, which is its test condition. And that means that you can get quite a lot. So if you happen to live somewhere a bit chilly, like minus 50 degrees Celsius, you're getting like nearly 30% more voltage. So let's come back to reality. Unless you happen to be at McMurdo Sound or somewhere like that in Antarctica, you're likely to be quite close to the 0 mark in New Zealand and Australia. So there's still some rise. And why do I not consider the fact the sun warms up the panels? It's because it's the highest possible voltage under any operating condition. And that actually can be a freak moment. For instance, it's a winter's day and it's cold and foggy and the sun has risen, but it doesn't penetrate through the dark clouds. So the panels are really at their minimum temperature. And then the fog clears and the beam of pure sunlight hits those east-facing panels and the voltage just goes whoop straight up momentarily until the panel warms up. But that instantaneous voltage is a hazard. So it's both potentially exceeding the voltage rating of the equipment, particularly the inverter's input voltage if it's too high. And also it's a safety issue. You may be trying to switch off the PV array at that moment and your switchgear can't even cope with that peak voltage for a short period of time. So we always talk about VOC max in our standards, never just at operating conditions. So it's the maximum that we're worried about. G'day, Jan. Nice to hear you I'll see you chatting to me from Sydney. Yay. So let's move on a bit. Okay, so I'm going to do a little bit of tech drawing now. So this is kind of explaining the IV curve and how it's affected by temperature and how it affects voltage and power. So let me just get my overhead camera up and set it in the right place. There we go. Okay, so let's start with calculating the highest voltage. Now, I keep going on about the fact that you can use a table 4.1 in 5033, but it's not in your interest. So across the bottom here, we've got cell temperature. And that's in degrees Celsius. And across here, we've got voltage. Now, there's a line which is known as the coefficient for open circuit voltage, and it's given in the data sheet for the product. So that's basically a linear relationship. So it goes like this. There's our line. Now, that's the amount of change, and you'll see that it's downwards. So as temperature rises, voltage decreases. So we're first going to look at open circuit voltage. Now, there's only one voltage you actually know from the data sheet, and that's at 25 degrees Celsius, which we call standard test conditions, or STC for short. There we go, STC. At this point, we have a a number we can start with, and so we can go across here and we'll have a voltage. Now, if I just jump back for a moment through my slides and see what it is. So for that panel that I just brought up, it was the Jinko 475, and its voltage open circuit is 42.54 volts. So here I'm putting 42.54. Okay, so that's the standard test conditions. Now the purpose of this exercise is to find out what that voltage will rise to under cold conditions. So let's just extend my little graph a bit more, and if I can get my pen to work. So we're just going to extend that out a little bit, and let's say it gets down to minus 5 degrees Celsius. Okay, minus 5. Now what we want to know is how much change in temperature is there between standard test conditions and the coldest operating temperature. So we go to here, we want to know the difference between here and here in degrees Celsius, and that's known as a delta T, change in temperature. What is the change in temperature? Well, it's actually 30 degrees in the negative direction. So we started at 25, we go 30 degrees in the negative direction, so we go minus 30 degrees is our change in temperature. Now we need to know what the slope of this coefficient is here, and it gives it in the data sheet as minus 0.25% per degree Celsius. So I'll write on there minus 0.25% per degree Celsius. So that times that tells me how much as a percentage of our standard test condition number we're getting as a change, and it will be an increase because a negative number times a negative number. So let me write it out. So therefore, minus 30, which is delta T, times minus 0.25% equals a change which is positive, and I bet you can do this in your head, but let's just show it on a calculator. It's always fun to punch in some numbers. So we'll go. Now, incidentally, a lot of calculators don't like multiplying negative numbers. You're right. So if you remember your basic arithmetic, that a negative times a negative is a positive number, you can just go 30 times 0.25, okay? And you know the answer is positive. So it's a 7.5% increase. So that's 7.5% increase in voltage open circuit from standard test conditions. We put a little STC to remind us we're adding it to the standard test conditions. So that number there, so therefore 42.54, and we're going to add to it 7.5%. So as a percentage, I'll just do that a bit more elegantly. So as a percentage, we'd multiply by 1.075. That's 7.5% times 42.54. So it goes up to 45.73. So 45.73 volts open circuit, and we call that open circuit max. And in this case, it's at minus 5 degrees Celsius. So there we go. We just calculated more accurately that number. Now, if I was to use table 4.1 from 5033, and I'll do this in red just to show you. So table 4.1 from 5033 will suggest that for that temperature, it would have a multiplier, therefore multiplier of 1.12 times 42.54. And let's see what the table gives us. 1.12 times 42.54 equals Now we're at 47.6, we'll round it up, 65 volts OC max at minus 5 degrees Celsius. So that's a big discrepancy. The real number, and I call it the real number because the manufacturer has given us the temperature coefficient. And by the way, 5033 lists in order the way to do this calculation that says using the manufacturer's coefficient, number 1. Number 2 is use table 4.1 from the standard. And number 3 is if the manufacturer gives a value for a certain temperature, you can use that. So if they actually gave you the -5 value, you could use that. But they never do. They always just give you the coefficient because they know that it can be simply worked out. So you might think, oh, that's only 2 volts different, Glenn. Okay, well, let's talk about how many modules you might have. Now, back in the old days, we were limited to 600 volts. And so when we were limited to 600 volts, if we divided 600 volts by 47.65, that would tell us, and round down, we could only put 12 modules in a string without going over 600 volts. And by the way, 600 volts still is an issue because most single-phase inverters do top out at 600 volts. Fun fact, I learnt this from an engineer friend of mine recently who designs inverters, is it's the reason for that 600 volt being so common even when you're allowed to go beyond it, is it actually makes inverters much more expensive because of the creepage and clearance and pollution requirements for going over 600 volts on a circuit board. So basically the PCB gets much more expensive to make over 600 volts. Clearances have to be enlarged. So yeah, it's about cost as well. So only 12 modules, but this is where the good bit comes, and I hope I'm right here. So remember, 12 modules under the old 4.1 table. Let's now do 600 divided by 45.73, cross my fingers, and we get one more module in a string. We get 13, and we don't exceed the 600 volt rating of the inverter. So there you go. It is really worth using the coefficient. Now, I can hear people crying out already, but my inspector uses the table. Well, they might well use the table, but you can always flash out a copy of 5033 and says, oh, but I can calculate from the temperature coefficient. And here's the data sheet, sir or madam, and could you please just confirm my calculations? So there you go. It's totally okay. You with me so far? All right. I'm just looking to see, we've got a few new people joining us. Shout out to me in the chat if you would. Just say hi, where you're from. If this is all bamboozling you, if it's interesting, I just like to know a bit of interaction. It's great. So let's move on. So that's all about, and I should give it a title, because this is going to be kind of a saved video. So we'll call it Voltage Open Circuit Max Temperature Compensated. Here we go. All right, so let's jump on to the next item, and which is, where are we? Go back to this. Okay, so we were looking at open circuit voltage, but now let's look at power. Why do we want to look at power? Well, this is when you're trying to do some estimates on a system's performance, because open circuit voltage is all about safety, but when it comes to how does a system perform, well, that's all about power. And so the module here is a 475 watt module. The little p, by the way, is just to remind us they're not real watts, they're peak watts at standard test conditions. The real watts are at the temperature that it will be operating. And now they give you a voltage maximum power. Here it is here, 35.21 volts. But that voltage will change with temperature. And how much it changes is the power coefficient. So it's the blue one down here, which is pretty close to the open circuit voltage coefficient. It's minus 0.3% per degree Celsius. So this one here is the coefficient we use for power. Now I'm going to draw a very similar looking IV curve, but you'll see there's a few changes. Okay, and a few rules of thumb that will come in. Oops, we'll get to that in a second. I'm jumping ahead there. Okay. New sheet of paper. Oh, sorry, Wet Cigar. So Wet Cigar is saying there's a lot of dropouts. I'm sorry to hear that. Um, yeah, it's hard for me to know because I can see my streams going out at 5 megabits, but maybe YouTube doesn't like it as well. But sorry, Wet Cigar, you're totally okay to watch it at the end when it's been optimized by YouTube. So yeah, could be a little bit choppy. It's weird. YouTube's telling me excellent connection. It's pretty strange. Looking at here. Okay, stream health. The stream is healthy. Just to understand that one. Anyway, I'm still learning this live streaming business, how to get it optimized. Just for those geeks out there, I'm on Starlink. And I've got good exposure to the southern sky here in Victoria. So, yeah, blame Elon if he's playing with the Starlink at the moment, launching a few more satellites. So someone who's got a really fast connection saying they're getting dropouts. Anyway, I'll press on. Let's talk power. So here's this IV curve again. Sorry, not IV curve. Relationship between temperature and power. So across the bottom here, cell temp again. There it is. And up the side here, power in watts. Okay, so we know what the power is at one point on this cell temperature curve, graph, which is at 25 degrees Celsius. Not doing power, I'm doing voltage. Voltage at maximum power. Sorry about that. A little correction. But I should point out that the change in voltage is directly proportional to the change in power because the current doesn't change. So if the voltage increases by 10%, the power increases by 10%. So it's directly proportional. So looking at the Jinko 475 modules, the VMP at standard test conditions is 35.21 volts. So we know at this point here, I'll do my little line again. So at this point here, do it in blue. We have 35.21 volts. Okay, that's the standard test conditions. Now we want to know under real operating conditions what the actual voltage will be at maximum power. Now 25 degrees Celsius is extremely hard to achieve when you've got full sun on a panel. Now the rule of thumb, this is where a little bit of guesswork comes in, is that depending on how a panel is mounted determines the amount of temperature rise from ambient. So rule of thumb is if the panels are flat on the roof, flat equals ambient plus 25 degrees Celsius. So they'll be 25 degrees hotter. If they're parallel to the roof and there's a bit of slope on the roof, you'll get some passive cooling, i.e. you'll get air movement behind the modules. And if it's freestanding, therefore like on a tilt frame, you'll get the optimum amount of passive cooling from any breeze as well as convection. And so freestanding, oops, I got these around the wrong way. That's 35. This is 25. Gee, that was a big mistake. So the worst case is flat on the roof, 35 degrees increase under full sun, parallel to a sloped roof, 30 degrees increase, and freestanding 25 degrees increase from ambient. Now, I should point out these numbers are rules of thumb, therefore they're not exact science, but I have actually, because I've got some test arrays here, and it's pretty close. It's not so close early in the day. It's all about when the sun is fully on the panels. So we are doing this calculation more or less at a time when the panels are operating at full sun conditions, 1,000 watts or so. So let's say it's a typical installation which is on a tilted roof with 150 mils of clearance under the panels due to the racking system, and that gives us 30 degrees rise. So 30 degrees rise from ambient. So what is ambient? So test conditions are here. let's say ambient is a sunny day in Brisbane, and let's call it 35 degrees is the ambient temperature. Okay. The cell temperature will be 30 degrees higher than that, so we're going to go up to 65 degrees is the cell temp. In full sun up here. So let's do the calculations on change in VMP, voltage at maximum power. So what we want to know is how much change from test conditions are we getting. So our delta T, once again, it's our delta T. So as you can see, it's 40 degrees of change, and it's a positive number. So equals 40 degrees C delta T. Now, we need to know what the slope is, and that's where we go back to our data sheet where it gives us the temperature coefficient for P max for power, and it's listed for these Jinko panels as minus 0.30% per degree Celsius. And that number times that number will give us the amount of voltage change on a hot day, a 35 degree ambient day with the panels inclined on a roof. So let's put those sums in. So therefore 40, a positive number, times minus 0.3% will give us, and in this case, like I said, some calculators aren't very good at negative numbers, so we can just remind ourselves that a positive number times a negative number will give a negative result. And I'm just going to enter these in as positives, so 40 times 0.3 equals, so it's minus 12%, exactly 12.0%, there we go, of voltage at VMP at 65 degrees Celsius. So how much voltage have we lost? Well, we started off with 35, so therefore 35.21 volts minus 12%. It's like doing your GST in reverse. So what do we get? Okay, so if I go 1 minus 0.12, so I'm multiplying that number by 0.88, which is the way of taking off 12%. So minus, times 35.21 equals. So the voltage drops down to just, well, let's actually round it off to 31 volts VMP at 65 degrees Celsius cell temp. There we go. So that's quite a big drop. And like I said, the change in voltage is proportional to the change in power. So we're actually getting a 12% reduction in power. So the other thing to consider is these are originally 475 watt modules. And so we're getting a 12% reduction in power. And therefore, they're actually only putting out 418 watts in full sun on a 35 degrees temperature day. This is something you could try and explain to a customer when they go, how come my 6.6 kilowatt system's not putting out 6.6 kilowatts? And you can bamboozle them with science, or you can just say panels lose power as they heat up. It's just the fact of physics. It's not dodgy product. I'll tell you what is good, though, is this number is getting better and better and better with every iteration of panels. So once again, solar panels are just getting more efficient, less loss, longer lived, cheaper, and even cheaper. It's a win-win-win. Okay, so there's my little graphs for the day, and Mark's saying it's pretty choppy for him. Thought it was my phone. Oh yeah, Mark, sorry about that. It looks like you'll probably have to watch the recording. So let's jump back to, where am I? Batteries. We're going to get on to labeling of battery systems. So bring up my labeling of battery systems. There we go. Okay, rearrange my table a little bit here. Now, I've been having a personal vendetta. In fact, hang on, let me just get big for a second. Here we go. I've been having a personal vendetta on inappropriate labels on systems, particularly battery systems. I see all sorts of labels splattered across the front of battery systems, and often it's whatever's in the kit. So you might get a battery kit, and it's actually for any battery system. And what do you know? Every label gets put on the battery system. And worse still, it's often just put on the front of a beautiful looking product. Imagine if you stuck those all over the door of your car. I mean, just because your car's got to have some labelling. It's not very much. Basically say what the fuel type is on the number plate. But imagine if you stuck that on the front of your bonnet or something. Well, the same thing with a beautiful looking BESS. You don't really want to stick labels over the front of it. And there is no requirement to. The standard says adjacent, okay, and viewable at the location that the system's installed. So there's no need to destroy the beauty of your product. It's also not necessarily good practice. A lot of surfaces of BESSes aren't really ideal for sticky labels. They might be a little bit oily or textured surface. So yeah, don't stick them on the product itself. You can just actually use a little sheet and make a little metal sheet and put them all on a separate sheet and screw it to the wall. Look equally elegant and not ruin the look of the product. But let's get into. Charles just gave a tip, everyone. He said he dropped the quality under the settings to 360p and had it running gooder. Lovely English there, Charles. Gooderer. I love that, gooderer. All right, so I'm not sure if that's going to help anyone, but let's push on. So table 3.1 in 5139, which is our battery standard. Now, for the Kiwis watching, until April, or hopefully April when it gets gazetted, it's still best practice advice. It's not actually a compliance requirement in New Zealand yet to comply with the battery standard, ASNZS 5139, even though the regulator has said to me personally, it could be used in a court of law as an example of best practice. So what does that mean? Well, it can't be inspected in an ROI of non-compliance, listing it because it's not listed in New Zealand electricity regs, but here in Australia it's been in force since 2019, so we're well used to it, but we're still doing the wrong thing, and that's what I want to talk about today. So getting onto my high horse here, let's start with table 3.1. The purpose of 5139 really was to address there was a lack of safety standards for battery systems of chemistries other than lead acid, nickel, cadmium, and nickel iron. So there was, really nothing about lithium in the old battery standard 4086 part 2. So we produced the standard, and we produced I call it a cheat sheet for 5 chemistries to give you a quick idea of what the hazards are. And from a hazard, you have associated signage, right? So you can see that the first 3 columns are mandatory for all chemistry types: electrical hazard, energy hazard, and mechanical. Mechanical is meaning it's heavy and it can fall on you. So when it comes to fire hazard level, we actually talked about that in the last Toolbox Tech Talk, so I'm skipping over the fire hazard, and I'm going to focus on the last 3: explosive gas hazard, chemical hazard, and toxic fume hazard. So let's start with... what's the one I'm going to start with is chemical hazard. Okay, chemical hazard. So chemical hazard for lithium ion is Na. So it's saying the lithium ion batteries are not a chemical hazard. They don't spill chemicals out of them that are hazardous. What does that mean? Well, because it says Na for chemical hazard, and how do you know that it's Na? Well, it says so on this table, and you can consider that. Hang on, I'm going to jump forward a bit, that if there was a chemical hazard from a spillage, you would have to put up appropriate signage for that hazard. And this is the sign that's really got me grumpy. It's the electrolyte burn sign. I see it so often on a lithium battery. So an electrolyte burn is a chemical hazard, right? See, it says clause 7.10, and clause 7.10 says all battery types categorized as a chemical hazard shall carry a sign specifying what to do. Blah, blah, blah. This shall be mounted either adjacent to the enclosure or on all doors of the room. It doesn't say stick it on the battery. Now, this is a sign that was produced way back for lead-acid batteries, particularly flooded lead-acid batteries, because the battery standard even says for valve-regulated not required because they don't leak electrolyte. So a valve-regulated lead-acid battery doesn't even require this sign. But going back a step to here, it says lithium-ion batteries are not a chemical hazard, right? Got that? Not a chemical hazard. Therefore, chemical hazard does not apply. You do not need to put the electrolyte burn sign on. That's pretty straightforward. I'm not even doing an interpretation. It's right there in 5139. And I should point out too that if you do, for some bizarre reason, put the chemical hazard sign on, you should also provide bunding to capture that amazing chemical hazard that doesn't exist. So bunding is like a tray typically underneath your beautiful looking BESS. So if you're going to stick that sign on, you are logically also saying there is a risk of a spillage and you need to capture that supposed spillage. So the short answer is it's not a chemical hazard for lithium ions batteries. Therefore, don't put the green electrolyte sign up. It is not required. Now, let's go back again to Table 3.1. Table 3.1 lists two other hazard categories for lithium ion. One is explosive gas and one is toxic fumes. Now, the toxic fume hazard's got a tick, so there's no negotiation. It's deemed to be mandatory. So that means you have to have a toxic fume hazard sign, and you also have to have, once you list the toxic fume hazard sign, the PPE required in case of release of those toxic fumes. And that's also poorly complied with. So I often see the toxic fume sign, but it doesn't say what to do. Like, put on a breathing apparatus with forced air, which is probably what you would need. Because if a lithium-ion battery is venting, the electrolyte as a gas, so that's lithium hexafluorophosphate, gets hot enough to rupture the case and start venting what looks like a white, cloudy fog. That's actually quite toxic, and it's forming hydrogen fluoride in the air and burning your lungs if you breathe it in. So because it's a gas, you can't just filter it out with a filter. You're going to have a breathing apparatus with forced air. So toxic fume hazard is mandatory, and therefore you need the sign for both the PPE and the toxic fume hazard risk, under what conditions that toxic fume hazard will occur. And it usually says fire. Okay, so fire. All right, so explosive gas. Now, we've got a note 3 here. Now, it's got a tick, which means it's mandatory, but then you read the note 3 and it says lithium chemistries that release hydrogen under fault conditions should be considered an explosive gas hazard. Fair enough. E.g., lithium manganese. For those not familiar with lithium-ion batteries, come in lots of chemistry versions. Lithium manganese cobalt, sometimes called NMC, nickel manganese cobalt to be exact, would be the one they're referring to here. But for stationary energy, lithium ferrophosphate seems to be the dominant chemistry, and it's not listed here as an example of hydrogen under fault. So how do you know? How do you know if your lithium battery produces hydrogen under fault conditions? Well, that's what the safety data sheet is for. So we jump over to the safety data sheet, and it says here, now it does say in Australia, oops, too many presses. In Australia, the safety data sheet for a battery system shall be included within a document holder at the main switchboard or meter box, and where available, the fire control and indicator panel. So it's not just a QR code on your site map or your equipment, it's actually a physical copy of the safety data sheet is required in Australia. And that physical copy needs to be in a document holder. Okay. I don't think I've ever seen one, except in my place. That safety data sheet should list all the hazards. So, do you require this sign? Danger, risk of battery explosion for lithium-ion batteries. Well, I've got the safety data sheet here for a LFP battery from, in this case, it's a Cygen store system from SIG Energy. And it says, main hazards, fire or explosion hazards. Lithium-ion batteries contain flammable liquid electrolyte that may vent, ignite, and produce sparks when subject to high temperature, greater than 150 degrees Celsius, blah, blah, blah. So it's a kind of saying there is an explosion risk. So I'd say that sign is required. It doesn't say it vents hydrogen, but I think it's pretty clear. If it says explosion hazard, you need to have danger, risk of explosion. So let's say that's pretty much a laydown Mazia now, and from my experience, that's the standard for most for lithium batteries. So unless your data sheet says no risk of explosion, you're going to require that sign. Okay, so I think I've covered everything on the safety data sheet side. Yes, I have. There we go. So, let me just open it up for a bit more chat. How are we going? Just a few minutes left. Any questions, anyone? I know it's been a bit choppy, says Mark and everyone else, but if you do manage to type a question in, I'm happy to answer it. I'm going to blame Elon for this one. I might switch back to my good old 4G from Optus for my next live stream. I've got two internet connections here. One's Optus and one's Starlink. And I was using Optus the last few weeks. Thought I'd give Starlink a whirl, but it seems that it's a little bit more choppy than the good old 4G before they phase that out as well. Okay, so, any questions, anyone? And for those who missed the beginning of today, I got a little bit sort of dewy-eyed about the fact that at last New Zealand is catching up with Australia for our solar standards, and New Zealand, the Minister for Energy, Simeon Brown, announced that the government will overhaul the neglected standards, and that includes our solar and EV standards. So when I say our, New Zealand's solar and EV standards, they'll come in line with Australia. So that's really great news. Cool. So I think I can't see any questions coming in, and apologies once again for any choppiness in the live stream. I do record this locally as well, so I'm going to just check it after I finish the live stream. And if it is a bit choppy in the YouTube version that's saved, I'll just upload the local recording. So once again, thanks everyone for joining me on Toolbox Tech Talk this Sunday, the 10th of November. Check it.